Chapter 9 is the study of rotational motion. And when we look at the concepts that are expressed here in your chapter, we have a few that we're going to try to point out. To study angular velocity and angular acceleration is one of our goals, and to examine rotation with constant angular acceleration, and comparing linear and angular quantities. So what we're talking about is an object rotating around an axis point, an axis of rotation. So they show you this irregularly shaped object here, rotating point P, rotating around axis O, or origin, and the angle then of that rotation is indicated with theta. Up until this point, we typically have been thinking about degrees, and at this time now we start changing our understanding of this rotation, converting it from degrees to radians. A couple of definitions here of radian are given in your text, showing that 1 radian is the angle at which the arc S has the same length as the radius, arc S as the radius. That's one definition of a radian. Another is that the angle theta in radians is the ratio of the arc length of S to the length of the radius. So theta equals S over R, which another definition of what a radian is. Angular displacement or change of theta, radians is the definition of radians in degrees. As I said, we used to think of, up until this point, we've thought of degrees. Now we're thinking of it in terms of radians, where 1 radian is 57.3 degrees, or 2 pi radians equals 360. Looking at it from a conceptual standpoint, a merry-go-round is a good example of how these two, the comparison between a linear speed versus an angular speed or velocity. I used to use a record player, or a record on a record player, but that doesn't seem to be as commonly understood by these more recent generations. But here you have the axis of rotation of the merry-go-round, the line axis of rotation to the children between the two. The linear speed will be the speed at which each person is traveling in a straight line, tangential speed. Obviously, the person on the outside of the wheel is going to be going at a faster tangential speed, or linear speed, versus the one who's on the inside of the circle. However, their rotation, the rotational speed, is the same in the sense that their angular velocity is the same, because they are traveling at the same RPMs, rotations per minute. The definition of the formula, or the way angular acceleration is expressed in formula form, is the alpha representing the average angular acceleration equals omega 2 minus omega 1 over the change in time. So here's 2 bicycle wheels, one obviously accelerating. The omega for 1, case 1, is going at this speed at this time, and then later you can see by the greater number of spokes it's going faster. That's the way they illustrated it, and has a greater rotational speed here and at this time. So by doing it, the difference of those two, and then dividing them, you can find out what the angular acceleration, average angular acceleration is. An example problem that's given to you in your text is on example 9.1. Here it's showing you the angles of the change of the angles here, giving you the angular velocity and the radius, and they solve this problem for you in this example in 9.1. So first you would need to convert your omega to radians per second, and then after doing that you would then find your angular acceleration by the change in W over the change in time. And they also link with you a problem similar to this one. And if you go to your online text, you can click and watch the video that shows you the working out of a problem very similar to this one. And so you might find that to be very helpful. A couple of signs of conventional practices here is that if something's rotating counterclockwise, it's deemed to be positive, and something rotating counterclockwise deemed to be negative, just as the normal convention of how we calculate these. The last thing I'd like to cover in this video is the comparison between the linear and angular motion formulas for acceleration. Obviously they're parallel to each other. However, you can see the change in some of the units that are not units but variables that are used to represent them. So velocity in straight line motion is equal to the initial velocity time plus the acceleration times time, whereas in rotational we substitute omega in for the angular velocity equals the initial angular velocity plus the angular acceleration times time. And so each of these have, it shows a nice parallel comparison between the linear straight line motion and the rotational angular acceleration. And I think that's a helpful comparison to have, and I know I've seen it be a benefit to students to have this written in a form that they could access and refer to.